And that's why we're getting also to the AI stuff today. What I'm focusing on is on the economics of AI, big data. That's my key part. And I want to get you through all parts of AI. What you see currently, and if we talk about financial aspects, let's have a look at market capitalization. We have roughly 1 trillion. It's getting a bit lower today because we have a bit of a crash. And we have to have a look why that is the case. There is only one aspect which is very neglected, and that's why I put the telecommunication part in it. Because if we wouldn't have any fibers, mobile phones, networks or what else, all this trillion value will be evaporating because you won't have any internet. You won't have mobile phones, which are for big data, and with Android, of course, one of the most important devices. So lots will be not there. And that's what I want to show you today. We have currently a new revolution in the mobile network in which we can connect devices autonomously. So the latest development I want to show you today is where we have really devices which don't need any battery anymore, which feed the latest ones from the mobile network, not only for the communication, but also for the power supply. And I want to discuss with you what the impact to AI will be. Let's have a look. Since we're talking about financials, how much cost it to connect something by a wire? So normally you have to let sensors have been wired, and that's an enormous cost if you want to put sensors in a smart city, for instance. Each wire costs you a very low estimate, €5 per meter. Each wire is roughly 30 meters long. That means roughly for the investment you have to do in a smart city, if it would be by wire, would be €150 per sensor. So you see we have for smart city a strong argumentation that we would prefer the sensors to be wirelessly. Because simply it's cheaper. As you see here, the cost part is getting there here. What I want to show you here is what we develop for kind of communication technologies which are wirelessly. So we have here in this graph, we have here the high bandwidth, low bandwidth part, and we have here the wide area, local area. So here you have very known technologies like Bluetooth, which have a low power variancy, of course, as well, which is local area and high bandwidth. And we have here a part which is the most interesting. It's called low power wide area, which means effectively I can connect devices all over the country. Many technologies are now getting available all over the world, which means high standardization, and high standardization means low unit cost, provided that the technology is cheap, but at least you get your benefits of scale. Here you have things like Sigfox, LoRa, and I want to talk about narrowband IoT because it's one of the projects I was in, and it's standardized all around the world. So we now have deployments in China, which is getting a very big mass market on sensors, if you know, and they use their narrowband IoT network to get the mass deployment of sensors. Why? First of all, what does it do? The technology enables a normal network to connect 100 times more of devices. And so we tuned the networks historically on mobile phones and some machine-to-machine communication, but we needed to upgrade the network to get a mass sensor deployment. Secondly, we went for low energy. So we now have tuned the network and the sensors and all the hardware as such that the battery can last for 10 years. And I'll explain to you why this is essential. Then, many sensors are in the street, or deeply in the basement, or in the cellar. They're not always there. So what we try to solve with changing the way we transmit, that we have, in general, are able to get sensors down to the basement and 2 stories deep. And then they still can communicate. So this kind of sensor So I brought to you all kinds of sensors we developed during the project. This one is of a firm in the Netherlands, TBGG. And this sensor can be mounted in the street and will detect, for instance, if a car will be parked above it. And we now in Hamburg, we're supplying the whole city with these kinds of sensors, and we have a total network in which we detect where cars are parked, what else. And so this is one of the examples we developed in the project with our partners. What you want to have, you have a bit of a drawback, of course, always, which means effectively, if you tune things down on power, you get down on your bandwidth. Is that critical? Yes and no. Many sensors just said, like the parking sensor, I have just parked. It's just a bit. It's very critical information, of course, but the amount of data to be transmitted is very low. What we try to do is get a plug and play. This is working as easy as your mobile phone. It's highly secure. We can't hack it because we use all the encryption which we have in a normal mobile network, and it's a worldwide standard. So you can scale it very easily and put it in your network and piggyback it because the bandwidth use is very low. So here you see we try to get maximum scale benefits by this kind of standardized technology. But we had another problem to be solved. Batteries. What is the cost of changing a battery if it is something is installed? Well, for most things you have to put a technician to the location. Putting a technician to a location will at least get you, if it's not mounted very closely to each other, it impacts your business case on cost on roughly 10 to 35 euros per battery charge. Which is, if you're going to massification of Internet of Things, of course, and if you want to automate buildings and put things in the streets, you have to dig it out. Which means it's even more costly because you have to block the street, you have to dig out the sensors, you have to put tarmac on top of it, so the 35 euros is getting probably a bit more. So, what we now do, and that's NAUI, which is one of the latest developments on energy harvesting, is that we effectively get sensors which do not use too much power. We use the mobile network to fuel it. So we're getting, in 5 years, in a world in which you have lots of sensors, which can be fueled from the mobile network itself, get the power from that, and at the same time transmit massively. So you see lots will be happening here in the Internet of Things, which is very relevant for an AI and get more value creation. And that's why we make a bit of a prediction of the penetration rate. So if you look at the automotive and a worldwide penetration, you see that not everybody's, but since it's introduced roughly 150 years ago or so, still not everybody has a car in the world. You see the telephone, if that's a fixed line one of the ITU, and not everybody has a fixed line telephone. Electricity went a bit better on penetration. Television, VCR as well. Smartphones are now getting more prevalent, but there's still a lot who haven't got a smartphone.
Very short question, or you put all the questions to the end?
We put the questions to the end if it's, I don't know what the format is.
We put the questions to the end.
Okay, perfect. So keep and open. What we see here, the Internet of Things grows now faster than we ever think before. The currently spent on all the things of Internet of Things is roughly 125 billion, currently already. And you see the growth rate is getting very rapidly. So that's why I want to make some attention to you, because I think as data scientists, these kinds of sensor information redevelopment gets relevant for your business too. Let's go to a case in which we have already impact of the Internet of Things and AI. In the energy transition or renewable energies, we have variable wind, that you see here. And these variable winds have an issue in a network. You probably know if you machine learning and do predictions about energy balances in the network. It's one of the cases you apply it. If you have power imbalance, your network is not going to be happy. What often happens is that they switch off the variable sources, the windmills, which is a waste of renewable energy. What we do now, and that's Eneco, which is one of a Dutch, not surprisingly, supplier for energy, which has windmills and has domestic applications. They now have built a switch on the Internet of Things, where effectively the Internet of Things switch on the boilers into the home to dissipate the energy. This causes effectively a few things. So we have the variable winds. If the machine learning detects, my network is getting unstable, we're not switching on off the windmills, but we monitor also the electricity network if it's stable enough. And there you see these kind of actuators here. This is one of the first series to be installed in the next month. It's simply be installed in your home, in the basement, where the boiler is. And in case we have too much energy supply, we simply switch the boiler on. And there you have a very nice source to stabilize the network. And since the whole water needs to be heated anyway, the energy is not weighted at all. It also got sensors here, in which is optimized the heating process as well. And so you see this is already getting so far. What you see roughly is the environment from this case, get the maximum benefit from the renewable energy. The provider has two effects. If there is too much energy, and in summer because of solar and wind power, you see effectively that we have lots of imbalance in Europe in the networks. And effectively energy is for free. If you, like Eneco, not only are in the energy business, but also in the warm water business at home, you heat effectively the warm water for free. Or sometimes you get even sponsored because you have a negative price on electricity. And for the consumer here, they have more control on the hot water. And so here you see the complete change of AI machine learning in the stabilization of the network. The Internet of Things play already a role. This is getting live in a few months from now in the Netherlands. We get further. Let's have a look at the bike. Sorry for the cliche, I'm Dutch. We see here that the bike business used to be a once-off business. You buy a bike for a once-off amount of roughly 900 euros or what else. Second hand, of course, cheaper. In Amsterdam, the price is undefined. What we do now, if we have a new Amsterdam-built bike, which looks a bit more flashier, which is Van Moof. And Van Moof has a tracking sensor with the mobile network included, which can be switched on purpose. So it's not tracking you all the time, it's only on demand it tracks. What you can do now is you can rent a bike. But not a normal rent, it's including the service, the repairs, and what else you always need to get the things up and rolling. So you get the key, you're being paid for a key as a once-off, and then you have a biking service. Why is IoT so important for the business model? Because since a bike gets lost, and you have a renting model, you want to know how it's getting lost. And therefore, IoT is so important to change this kind of rental models. And so you see, we also get a very big change in the model, in the way we do business, because IoT and AI enabling very different models in order to be the economy. For Moof, I just keep two examples. We also transform insurances. So normally in the Netherlands, probably in Luxembourg, it's the same if you buy, not as much, but in the Netherlands, you're well advised. If you buy a new bike, you buy an insurance with it as well. Because the risk is that it will be stolen is quite high. What happens now is Van Moof, because of the tracking service, make a bike availability guarantee, including a insurance. So if you get back lost, it will be tracked and traced, and if it cannot be found again, you get a replacement bike. How the business model works is you get the insurance fee as a bike manufacturer, so you can shift in the value creation to the bike manufacturer from the finance industry. What you also see is you get a bike as a service as a model, which is totally different, because as insurance you most of the time have to buy a new one. And so there you see also a total shift and change in business model. Of course, and now I get to the sponsor, we have also changes in the way we do business. So novel interfaces we create with the speakers also enables you to get totally novel business models. Because effectively the way you interact with the customer is different. And since the way you interact with the customer is different, you get very different business models. So it's very nice to show you all the technology. If we look at AI and society, much of the things we do is by the acceptance of society. And last year we wrote a paper for the German government. And in that paper of Bitkom, we asked the German population where it's useful to put AI into practice. One of the first examples is to mitigation of traffic jams in town, which the German population thinks this is relevant. Another one is to alleviate heavy work in industry. You see car country plus industry country. And so you see it's cultural. Acceleration of administrative activity, so the bot process and the robotic automation is here paying in. They hope, as currently rated as the most innovative country, to have a better capacity in R&D. And we have things like customer service getting better. And so that's also robotics, robots, and everything we do there is also the speech interface, which is highly developing with AI. How you make economics. And that's the work, I modeled lots about it, and I have some papers with it, of Springer and everything we published on it, is that we have, in general, if you look here at our famous data lake, and we have here our algorithms, to be very simply, we have two elements which give, in general, more value creation. We have the better information than before, but knowing things better is not relevant. It's very nice to know things better, but you're not earning money. The other thing is what we call decision agility. So what you do is you put information into processes in order to optimize the process, and having a better decision with a better process, you get a value creation. We give an example. So one of the startups we guided in the mobile network is Epacomat. So you have two kinds of solutions here. We have the IoT solution, which is putting the sensor in the street. We can also do analysis on the mobile network and what the density of communication is in some places. By doing so, I can see the behavior in a network where car will be parked and where empty spaces on the street curb. The accuracy is roughly of the algorithms Epacomat, that's a startup of Deutsche Telekom in the Czech Republic, is roughly if you're looking for a parking place on the street. And so it's not in the parking garage, it's on street parking. And I said, okay, the space is free and I want to drive to it. You have roughly an 80% chance that you find an empty parking space in the area indicated. So with parking sensors it's getting, of course, very accurate, but with this kind of AI-based and machine learning kind of event, you see effectively it's getting much better. They developed an app, you book it, so they have a revenue model based on the booking process. You can rent in the car, it's totally automated. And what you see here, in general, in the model, we get better information, we get real-time parking and available parking spaces. That's the better information you offer. We have decision agility, which means we have agile navigation to free parking, start driving around, which seems to be at this campus also an issue. And two, we have also very easy parking fees payment, because effectively it's based on duration. And therefore, It improves in the parking experience, is the benefit. It reduces time and effort, and the cost, of course, and of course is very important to the environment. And that's why the thing gets in. Because we now get a handover, we have, of course, then talk about the cooperation between humans and machines, because it's also a very important aspect. And Dominique doing his research on that one.
Thank you very much, Frank, for the interesting first part of the presentation, and good evening from my side. I would like to pick up the ball and talk a little bit more about the value creation of artificial intelligence. And the value of AI is created by combining the strength of both human and artificial intelligence. Our strength as humans are, for example, to perceive unexpected stimuli, to develop new solutions for problems, or to deal with abstract problems. Very important, we are able to change and we can learn from experiences which AI cannot. On the other side, there are the cognitive strengths of artificial intelligence. And AI is way better than we are in specific fields. For example, AI can perform repeatable tasks accurately. AI can store huge amounts of data, which we cannot. AI can retrieve the stored data reliably, and also very important, AI can perform simple calculations quickly. Both sides, or the strengths of artificial intelligence and humans, are valuable, but they can be more valuable when they are combined. And that means that AI and humans have to hand each other. They have to interact with each other. And key to understand how this interaction impacts the value creation is to analyze commercial processes, or in other words, customer journeys. A customer journey is the sum of experiences that customers go through when interacting with a brand or a company. In literature, there are several models that describe or define customer journeys. And one model, which is shown here, defines a customer journey along these 5 phases. In the awareness phase, a customer has a need or gets to know a need, and he gets to know possible solutions that fits to the need. In the consideration phase, the customer thinks about buying a specific solution. In the purchase phase, the customer buys a solution and uses it in the usage phase. In the retention phase, the customer is satisfied or even enthusiastic with a product or a solution and will buy the product again and again if he can. Along the customer journey, there are also touch points, which are points of contact for companies to address customers and to provide detailed information to the customer to push the customer along the customer journey. Touch points in the awareness phase are, for example, TV, radio, or print media. In the consideration phase, there are social ads, reviews, blogs. For example, we have a store or website in the purchase phase. In the usage phase, the product itself can be a touch point, and we know it all. In the retention phase, there are newsletters or loyalty programs. Frank and I assume that AI and IoT impact customer journeys or improve customer journeys in the future, but the question is, how do AI and IoT improve customer journeys? And this is exactly the question which I'm dealing with in my master thesis currently. And to answer this question, we have to look very detailed into the details of AI and IoT customer interaction. And that's what we did. We analyzed several customer journeys for different use cases. For example, smart parking, as Frank already mentioned. And smart parking uses AI to find free parking spots and to navigate the customer to the parking spot. Another case we analyzed is shopping via a dash button, for example, Amazon's dash button, which allows customers to order goods, just by pushing the button and confirming the order afterwards. And this makes the customer journey more simple and time-saving, for example. Other use cases are shopping in autonomous stores, for example. I will come to that later. Or shopping with recommendations. You all may know this. On the Amazon website, for example, there are recommendation engines used to push the customer to a purchase. We analyzed TV control via voice assistants, and we analyzed a new service of Deutsche Telekom, which is the voice identification that allows customers to identify with the voice instead of a 8 digits or 10 digits customer or contract number. These analyses have shown that artificial intelligence and IoT impact customer journeys heavily. This is a selection of our results. And the first one I would like to mention is that AI and IoT have the potential to shorten customer journeys and to save time for customers. The second point is ease of use, meaning that AI and IoT eases the commercial process, which leads to a better customer experience. We have customer lock-in. Pairing the consideration set to one brand can result in a monogamous engagement between customer and the company. We have a personalization, which means that with a targeted address of the customer, a positive experience can be created, which is also the fact with automation. Automation makes it simple and compelling for customers to move from one step in the customer journey to the next step. We have a faster purchase decision as well as increased prediction power as results, and also important to mention service improvements. Services can support customers proactively when using AI and IoT, and they are available 24/7, which were not available 24/7 before. One example for a service which is available 24/7 is the autonomous store from DeepMagic. And DeepMagic allows customers frictionless shopping, where you can simply enter the store with identifying with your credit card, choose a product, and leave the store all the time. And all goods you choose and take with you are charged to your account automatically. It is important to know that any of these insight-driven business models will only function sustainable when you treat customers and act in a trustworthy manner. Therefore, ethical guidelines are essential to uphold trust. As we, Detikon, are part of Deutsche Telekom, we put Deutsche Telekom's AI guidelines here, and we advise you to follow these guidelines when dealing with artificial intelligence. Let's go through the guidelines quickly. We at Deutsche Telekom are responsible, we care, we put our customers first. We are transparent and secure, and we set the framework. We maintain control, we foster the cooperation model, which is the topic I talked about earlier when I mentioned the interaction between AI and humans, and also important, we share and enlighten about what we do. And that's one reason why we are here today. I'm now at the end of our presentation, and if you would like to read further on these topics, as Frank mentioned, we have selected articles. We are looking forward for your interesting questions and try to answer them as good as possible, and thank you for your attention.
Okay. Let's go.
Yeah, there is a plot about for different technologies. And I understand the penetration means just the percentage of population.
Adaptation, so roughly, yeah.
Yeah, how come electricity went over 100% then?
It's actually, if you calculate also the electricity by batteries, voltage, And what else has been out there? And so you see, if you go to Africa, lots of solar panels. And so we not only put the grid, as here is one of the numbers in this kind of statistics, but you see if you are all around, there are very little places in the world which do not have a supply of some sort of electricity by batteries or what else.
Okay, but I mean that it's not just 100%, it's over 100.
Yeah, that's roughly PowerPoint, because we put, as you can see, the presentation on a computer, and we had some rendering shifts. So you will see so we have a PDF you can share, but you will see in general that our slides were a bit shifted because of the change of computer and script, but it gets roughly to 100% because everybody has electricity in some sort.
So to summarize, it's 100, is it just the slide?
That is 100. In some of the statistics, so for instance, if you're looking at mobile phones, sometimes I carry 2 mobile phones. It means effectively I can get a higher penetration if you are very academically sound. But here it should be 100%, so everybody in the world, or most people, have some sort of electricity available currently. Be it a battery or a solar panel or what else, it's getting very prevalent. But it took a long time.
Okay, thanks.
You're welcome. Other questions? We would like to address. So.
Say then we can hand over the microphone to.
Correct.
One question.
Yes, please.
What happens with these sensors when you want to change the technology? You need to change all of them.
Not really, because even if you have a very old phone, it is on most technology backward compatible for a very long time. And so many people still have, which elder people keep their phone for 20 years. They just switch on and they are backward technically compatible.
So they're being designed with what kind of a lifetime in mind?
Technologies is roughly 20 years.
20 years. Okay.
And so you see now we're phasing out things like the analog network. It has be around for the digital one for 40 years or so. And so if you look at ISDN, it has been around now for 40 years when it started technology-wise, roughly. And so telecommunications technology have a very long backward compatibility. And therefore we never know what happens in future, but historically it is very long, for long run, backwards compatible.
Perhaps I'll ask one more question. The plots actually, they look quite interesting. There are some more, maybe the question is not a question to you, but I just see that some of the plots have some somewhat unexpected falls.
We have a application which is ThinkCell. So what we did is when we made the graph, and we made it 3 years ago, I think, with the narrowband IoT project, to just give a bit of a sense what's happening. And there, so I cracked the numbers myself, and you see here that some events in society, like wars and what else, which went through the period, has dips in a adaptation curve. So if you're looking at a long time, for instance, you have crisis in the economy, and things went back. We have, of course, parts of the population. Sometimes you have a population growth or decline. There's a minimum effect, but you see, if you look at the ITU figures, which were maintained for 150 years, we have many effects due and events in the world which were impacting, of course, the society. Since it's 150 years back, there was lots of going on. And there you see that the ITU has bumps and bubbles in it.
Actually, I suspected that maybe those related somewhat to some.
Yeah, it's probably so. Because when I was cracking the numbers, I can remember, I think, hey, it's going down, and then it was in the years around the war, and then effectively the penetration went down because the whole network was destroyed in some countries.
Because I see that the phone popularity, for example, dropped. If
if I see
Yeah.
it correctly, somewhere in the late 20s.
20, it's Second World War, First World War, Second World War. So when I correct the numbers, but please, it is 3 years ago. So what I recall is that it was around either the First World War, so in the 1820s, sorry, and in the 1940s. And then we have actually a decline in fixed-ness telephony because much was destroyed. And the ITU was measuring that very accurately. And so that's the reason why you have dips in this adaptation curve. Happy? So that was when I cracked the numbers and I recall the best.
Maybe we take one more question. Or
Please.
Are they short or?
And we are around, so.
Good. So maybe one more and then we take it offline. Maybe you want?
Sure. There's a fairly quick one. So there's, I mean, you gave that matrix earlier of like, wide area, low power consumption, and so on. Is there, so, I mean, obviously there are some applications such as like indoor localization or whatever that might have high power consumption, but you still want it to be autonomous and, wireless.
Yep.
So, for that space of technologies, would you prioritize improving like battery technology, so energy density, or would you prioritize making the device? It
depends on the application. So, of course, we have so if we took the Google Glass and put it into real-time video, which is one of the applications you have, which is in the ground, it must be small, and it must be hand bandwidth, for instance. So if the battery is not lasting, you're getting to a hub concept, which is a mobile phone. That's one thing you're getting out. So you cannot tune everything to the perfection. Many of the broadband applications, however, are always attached to a car. Or if you talk, one of the aspects you use bandwidth, or at least low latency communication, is of course autonomous driving. Because your car needs to be stopped very quickly. And therefore those low latency applications, of course, are often combined also high bandwidth. And not always, but they mostly correlate with each other. And most of those things, as we discovered now, so we have in Nuremberg, an Autobahn, in which we test with the mobile network autonomous driving and how the behavior of the network is. And so we do test, as you can see, many of the cases in practice, in course, it's very new. And there you see, is a car attached. But if you say, okay, I have my glass and I need something small, you need a hub in which you get a local high bandwidth communication. Because the distance is shorter, it often uses less power. And then you need a mobile phone and then you connect to the network. And so that's a hub technology. And so when Google Glass will be powered by the mobile network, we'll see. But it will take a while.
The hub model is more like a stepping stone.
Yeah.
Okay, so then thanks to speakers again and for being here.
Yeah, Bon.
And thanks for coming here. And we're now handing over to Valentin. He's working on the Luxembourgish high-performance computing cluster, and he's going to share with us the details of setting it up and managing it. So, we'll make a bit of
That one off.
It's a PDF on the desktop.
Yep. You get tabs.
Just
It's a presentation one.
this.
Okay, you got that one.
And then we do.
The
It should be just
that
this
one. Correct. Perfect. You're up.
Ah. Not yet.
F7. Because it put it on dual mode. 1 second. Here. Got the screen. Got on duplicate. Duplicating. Enter. Yep, you're on.
That's good. Perfect. So, good evening, everybody. I'm Valentin Plugaru. I work at the University of Luxembourg now for 4 years. I was a student here before, since 2012. So, I'm going to first. I want to thank for the invitation, the organizers. They were very kind to reach out in the first half of this year, and we said, okay, we may have something to announce in the later part of the year. So, this is the later part of the year. So, here I am. So today we will talk a bit about HPC, HPC, big data, and AI, and I'm going to give you an understanding of the infrastructure that comes below all of that. So first, a few words about me. So I'm a computer scientist at the University of Luxembourg. I'm in the team of Professor Pascal Bouvry in Parallel Computing and Optimization Group. My core duties are on HPC facilities management, and what I do during one day, I can have 5 hats. I can be either designing a system that will be there for researchers in the next year, or talking to people, helping new groups come to understand what an HPC platform is, how they should use it, what's important to know about it, and so on, and building relationships and trust with stakeholders, including partners from partner institutes like LIST, LISR, which are in the research landscape of Luxembourg, and also with HPC vendors. It's very important to know your vendors that are there for HPC, because finally you're going to need to know their roadmap, what you can plan for the future, and that basically drives the kind of things that you're going to get in the future years for your users. So it's very important. And of course, knowledge transfer. So apart from onboarding, I'm teaching the master level here in the mix, Master in Information Computer Sciences, and we do HPC workshops. Actually, we have 2 of them per year. One of them was in June. It was a big HPC school of 2 days. One of them will be towards the end of November. So if you're part of the university, and I know some of you are, you're going to get an announcement of that. It's going to be held in Belval, in the Belval campus, where we are located for 1.5 years now. And it's also the good chance for you to understand about the HPC platform and actually to start to operate on it if you have not done so already. So actually, some of the students that passed through our hands were here and presented here in the past sessions, and that was very interesting because we saw what they were doing on the platform years after we talked to them and so on. So that's also always very beautiful. So on my side, I'm involved in ETP for HPC, which I'm going to talk a bit later about in PRACE. I'm one of the national delegates for sustainability forum by IT for ISO through ANEC and ILNAS, and hopefully will be part of the National HPC and Big Data Competence Center that I'm going to talk also a bit about later on. So for now, to make sure that everybody's on the same page, let's go through some preliminary, what HPC is, what big data is. Why are they essential? So we're in a data-driven economy context right now. So all scientific disciplines, or most, if not all, are becoming computational. So for that, you need some computing power behind, some storage capacity to take care of those needs. And the industry, the big companies already have been doing HPC for a while. Smaller companies, not yet, but they're being driven to this. Why? Because they're using HPC to reduce cost, decrease time to market, and become more agile. So that's comes finally to good finance sense. So HPC right now is a global race, and it's a strategic priority for most continents, if not only countries. And the EU is taking up the challenge. So there've been over the years several initiatives on this, like PRACE, the Euro HPC that I'm going to detail in a bit later. There's been a common project of European interest on HPC and big data in the past, and so on. So things are moving in HPC in general, and if you've been reading the news, you've already heard about Euro HPC for sure. To make sure everybody's on the same page, this is the slide for that. I'm going to talk about gigaflops, teraflops, petaflops, exaflops, so we need to know exactly what is where. Your laptop right now, even your phone right now actually, is on the gigaflops level of computing power. A server that you may have in the basement would be on the teraflop level of performance. A petaflop level you would call a supercomputer, a tiny one right now. And exaflop is the next big challenge, The next big challenge that was slated to be there for 2020, and maybe some countries will be able to achieve this. It's not yet clear, but it's a very competitive scene, so somebody will achieve it sooner or later, and it's going to be very interesting. And for storage capacity, gigabyte level, terabyte level, you have it in your laptop. Petabyte level, well, not in your laptops right now, but soon, hopefully. Exabyte level, maybe Facebook or Google already have this capacity. Well, maybe likely they have this capacity. And for the transfer rate, so we of course have a transfer rate which is megabytes per second, megabits per second, gigabytes, gigabits per second. And some other metrics are very important, like for read-write speed, IOPS, number of I/O operations per second that you're able to do, and so on and so forth. So we finished that. Good. Computing for researchers. If you want to do some computing right now, what do you do? Well, first of all, you take your laptop, you write some code, and you run it on your laptop. Your laptop is not enough. What do? Well, you go, let's say somebody else prepared some images, you're still able to run them on your laptop. Your VMs, your containers are not able to run it. Where do you go to? But you go to cloud. So one of the sponsors here is Amazon, so they will see their nice logo over there. So of course you have different levels of cloud services. If you want to be close to the bare metal, you're provisioning your full software stack on top of a IaaS platform. If you don't care about that, you just want to bring your data to an existing application, you're on the other edge of the scale. And if you need even more performance, and be aware that you can do HPC on the cloud and so on, we're going to talk a bit about that. But you also have the capability to go to an HPC platform. And an HPC platform is there to bring you the best kind of speed up, the best kind of scalability, and the fastest time to solution that you could possibly get. An HPC platform is not your laptop. It's not a cloud. They shouldn't be treated the same. And in fact, we give this as an example every time. You treat an HPC like a Formula 1 car. So you see in the pretty picture what happened. Well, the Formula 1 car was not driven so well, so it crashed and burned. Well, hopefully the driver is fine. But an HPC platform is very much like that. It's able to give you the best possible everything, but you need to know how to drive it. So it relies on ultra-efficient hardware. Networking is basically what separates an HPC platform from just a bunch of clusters glued together. And this does not mean that the three approaches, the PC, the cloud, and the HPC platform do not work well together. No, they work really well together. You can have your IoT sensors put the data in the cloud. When you need to do a prediction and you need it in the next 10 minutes, you bring the data down to an HPC platform, you compute on that, and then you give back the result. And the result finally is hopefully a nice slide on your presentation on your laptop. So different kind of HPC needs have different kind of requirements from the hardware, basically. Number of cores, the speed of those cores, how many operations per second they're able to give you, the storage capacity that you have, the I/O performance, the network latency, the network bandwidth. They're all important, but for different kind of domains, they're important in a different way. So for bioinformatics, for example, for life sciences, they don't care so much about the number of cores. Some applications really do not scale. Well, do not scale yet. They haven't yet been developed with the correct parallelization and so on. But they do care about individual per core performance. They do care about storage a lot and about, of course, the I/O performance. We are talking about AI, machine learning, and finally deep learning. Number of cores, well, in this case, if you're on a GPU, the SM units, the individual units, the more you have, the faster you compute. I/O performance is also very, very important. If you wanted to be able to drive your GPU's computing part, your storage system needs to be able to feed all of that data to the memory of the cards. So then you need a lot of I/O performance as well. Then IoT fintech. So if you're doing high frequency trading, guess what? Having a lot of storage capacity is not so important, but being able to say, I want to buy these shares in the next 20 milliseconds, then network latency is very important. And in high frequency trading, a lot of people, what they do is that they put the data center as close as possible to the trading center, such that the distance, well, the speed of light is the speed of light, so you cannot go faster. So you need to be close to where that happens. So for fintech, for example, that's an important concern. And if we glue all of them together, your HPC platform needs to be able to take care of all of those needs. This is what I would like to show. And finally, to bring this back to finance, the facility that brings all of that together, well, it has a total cost of ownership. And to talk about the total cost of ownership, what do you have? You have the HPC system, you have the storage, compute, and network. You have the staff, the systems people, the user support, the service management people. You have the power and cooling, and the data center costs. Is this everything? By the way, you're not allowed to ask me questions, but I'm allowed to ask you questions. Okay, so you see there's a lot of white space in there, so this is not all. You also have security, physical and cyber security. You have resilience. If one of your power supplies dies in one of your computers, which is part of a network of 50 computers, which is doing some computation working on for 2 weeks, and that power supply is the only one that you are having in your system, guess what? You're going to have a bad day the moment the magic smoke comes out. So you need to resilience, both at the system level and at the service level. You need to monitor your equipment, you need to measure your service, you need to report on that service, you need to do a procurement. If you do a procurement for €1 million, how much does the procurement itself cost? It can be up to 10%. Huh? So that's 100K just in the procurement, just to meet with the vendors, just to draft the specification, just to have the person months involved in the procurement process. Then with, of course, the supplier management and so on. To commission and decommission things, it's really not easy. But an HPC platform can be there for a long time, but at some point you need to stop it because the running costs of the energy is much more than buying the new version, 2.0. And that's not all. There's still one more block. So you need to think also in terms of insurance, warranty, support, maintenance, data management, software licenses. Guess what? You bought a new platform, has some new hardware. Maybe your applications do not work correctly. You need developer time. That goes into your total cost of ownership. And finally, documentation, user training, and support. Without these, your platform is unused. One rule of thumb, by the way, when do you go to cloud, when do you do your own in-house HPC is 50%. 50% of usage. If you can, over 1 year, for example, say you are above 50% of usage, then it's cheaper to run in-house. And a good, well-tuned system with a lot of knowledgeable people behind able to drive it, it's used between 60 and 80% at any given point. What this means is that you still have capacity to absorb some peak load, so 80 to go to 100%, and you're not wasting the equipment that was bought because you're below 50%. So, HPC components. We all know what CPUs are, what GPUs are. There's some difference in cost. Basically, some codes are well accelerated. They can take advantage of GPUs, some not. There's still CPU parallelization only, but this is changing nowadays for sure. A lot of people are not taking into account when they write code about memory hierarchy. Memory hierarchy is even more important than the kind of processor you're operating with. You have to be able to drive the data to the CPU. The CPU has its own registers, which are the fastest. If you're able to operate only with the registers, that's fine. Normally, you need to bring some more data in there. You pass through different levels of cache up to the memory, up to the disk. As soon as you touch the disk, your performance is not so good anymore. And that all becomes money because you see, the local node will have some local disk, but if it's not an SSD, then you're not getting the good kind of performance. But then if you try to bring 2,000 SSDs in a system, well, guess what? It's going to cost some money. So an HPC, one of the very basic things of an HPC platform is that it doesn't have the same kind of network as you would expect. Well, actually it has, but it has more than that. So in an HPC platform, you're going to find gigabit Ethernet, 1 gigabit, 10 gigabit Ethernet. That's going to internet and coming back. So if you pull from GitHub, it's going through the 10 gigabit network. Then you have InfiniBand, which is HPC-oriented, HPC-tuned networking link, which has less overhead, but is just faster. You see, the latency is just much, much faster then the equivalent 100 gigabit Ethernet. InfiniBand EDR, by the way, it's 100 gigabit. So if you're running an application, it's a tightly coupled application, which means that you have a problem and you're splitting it among distributed memory, well, many servers together. You're operating on it. Those distributed parts of computation need to communicate with one another. Then you're bound by the network. And then you want the fastest network that you can get. And right now, the two fastest ones that you can get are the Intel OmniPath at 100 gigabit per second, InfiniBand EDR 100 gigabit per second. And there are also custom networks. Custom networks, which, for example, in the top 500 supercomputers in the world, represented, well, last year, 13%. So they can be really dedicated networks or rebranded ones with special ASICs, special tuned systems. This I'm going to pass very fast. Normally, we try to use a closed network of fat tree, which basically means that between any two computing nodes, you have the same bandwidth. So it's a fat tree because you aggregate more links and more links when you go up, such that you have the same number of the same bandwidth between any two nodes wherever they are connected to the network. Well, this has some limits. So in practice, once you reach 648 network devices down, then you need to put another island, and then you do have a blocking network. You're not able to, well, not easily at least, or not cheaply at least, to do a fully unblocking network with more than this kind of number of ports, for example, number of nodes. Then in an HPC environment, guess what? You don't have Microsoft Windows. Well, you used to have BSDs. You used to have Unix, bare Unix, not Linux. But nowadays, it's fully Linux, and the reason for this is, one, it's stable, and two, you can really develop what you want on top of it, or go deep inside and cut what you don't want from it. So development flexibility is very important, all kinds of devices and so on. And many devices now are running Linux, even if you on your laptop are using Windows. By the time you open CNN.com, guess what? You're passing through 1 million Linux devices. So basically, when you're going to connect to an HPC platform or at least a supercomputer, it's going to be Linux in the back. So that comes to some learning curve, which finally which is there. It hasn't disappeared, even if democratization of HPC has been something that we've been trying to go towards. But well, some things need to be learned yet until you are able to drive this kind of a platform. So for the software stack, for example, the university is using a almost fully open source software stack, using SSH to connect to the platform, LDAP for an IPA in the very near future for identity management. Then the resource management, you submit a job, the system allocates it somewhere, a scheduler allocates it somewhere in the set of nodes for you. That's the resource manager, the job scheduler. We're using OR on the Gaia cluster, Chaos cluster. By the way, Chaos cluster is located 150 meters that way from here. And Gaia cluster 30 kilometers towards the south of the country because it's in Bilbao. And the Iris cluster, the newest cluster that we have, is also there, but even in a newer data center that I'm going to be able to talk about once I reach the slide. So you have all of these layers of software that enable you to connect to a platform, to manage the user base, to deploy nodes. This needs to be automatic, by the way, because I don't want to be the one bringing the CD to 150, 180, 200 nodes. Then you need to manage the environment for the users. I mean, with users, it's sometimes scientific software is very complex to build and install, and you need tools for that. And finally, you need to monitor the platform. So there's a lot of tools, open source tools, very good tools for that. And we're using Nagios, Ichinga ourselves, Ganglia, and so on. If you go to uni.lu, you're going to find all of this, by the way. So how do they look like actually in practice? These are disk enclosures. You can go up to 84 disks in a suitcase. Well, it's going to be a very heavy suitcase, by the way. But you can do that. The cost is 120k euro, more or less, with many. Okay, that's a very rough number, but it's there. Then on top of those disks, of course, you need to have a file system. There's normally on an HPC platform, you find the parallel distributed file systems, GPFS, it's called now Spectrum Scale from IBM, and Lustre. And by the way, we're using both, and we're achieving around 10 gigabytes per second in read and write from both these file systems. On Lustre, we're about to go to 15 with a bit of tuning from the vendor. And that's basically going to be quite a bit faster than your personal laptop. And all of these elements are going to go into a data center, right? So the data center, there is a very big difference between an HPC data center and a traditional data center. Why? Because the density of power is just much, much higher than what you would have in a traditional data center. So for networking racks, normally you have 5 kilowatt. For storage, 15 kilowatt. Well, guess what? To put a lot of computing power together, you go from 30 to 120 kilowatt. That's something. In the space of a fridge, you have 120 kilowatt of power. So to cool it, to power it and to cool it, it's very, very important to be efficient, because otherwise the cost, what is the cost? If you have 1 megawatt facility for 1 year and 10 cents of cost per kilowatt hour, how much does it cost to keep operational? 870K per year. So that's not negligible. So you need to be as efficient as possible. So one thing that is always being shown is this PUE factor, where you divide the total facility power, how much power you bring into the system, and how much of it is actually used for computation. And in a traditional air-cooled system that is really, really not efficient, you're getting a factor of 2, meaning that you bring twice more power to the system than you're actually using to compute. And you don't want that. You want to be close to 1. So there is a cooling technology called direct liquid cooling, which brings hot water up to 40 degrees to the system, and then it goes on top of your computing nodes, or very close to it. So you're able to cool things more efficiently. And then your PUE can be down to 1.04, I think is the world record, maybe even a bit less right now. So that's finally relates to your cost. So running the facility involves the data center. It's very specific for HPC, computing elements that we've seen, storage elements, a very big software stack, automated management everywhere, and above all, people to be able to drive it, to create it, put it in place, and users that are knowledgeable enough to run it. So what does the university provide in terms of HPC? Well, people, domain experts, computational scientists, data scientists, various research units have research scientists that are operating on the HPC platform. There's research groups which are developing their own code and accelerating their code on the HPC platform. And of course, part of the team that I'm in, we are doing the HPC clusters themselves, so managing them. And we operate together with the networking people, the IT of the university. And for example, for the facilities in Belval, it's managed by Fonds Belval. I think you all have heard the name. And we do, above all, we try to educate people into actually using this platform. So about the platform, a couple of words. It started in 2007. It's much more different now than it used to be. It started under the responsibility of Professor Pascal Bouvry and Dr. Sébastien Varrette. I joined much later myself. We are 5 people now operating it. At any given moment when you write an email to HPC sysadmins, you're going to get one of us looking at it, maybe several of us looking at it at the same time, maybe several of us replying to your mail at the same time, which can create some confusion. But that's fine, because finally your needs are the ones that are important. And together with Goodyear, well, Goodyear is an industrial-oriented HPC facility where I think right now we're going to be the same kind of size, if I'm not wrong, but we're oriented towards research science and education, of course, in an academia environment. By the way, several masters here provide courses and so on, and they're part of the projects they're operated on the HPC platform. Altogether, let's say we have some 600-something compute nodes from different generations, of course, and at the end of this year, we're going to reach what is a nice 1 petaflop milestone between all the kind of elements. And in terms of storage, we're almost at the level of 10 petabytes of storage across many storage elements, of course. So how do they look like? Well, they look like this. This is, for example, for the storage elements in CDC, in the Centre de Calcul, in the computing center in Belval. And who are benefiting from this? Like I said, it's the university, first and foremost. The faculties, the HPC basically it's a horizontal service across the 3 faculties, 3 interdisciplinary centers. And the work that these people do come together, we counted actually, around 23 computational domains. And most of them are in perfect alignment with the strategic research priorities of the university. So for different kind of needs, of course, we have the unique platform with regular computing elements, but also special systems that target specific workloads, like machine learning and AI. And this is the part that I wanted to wait the second half of the year to announce. We're going to get at the end of the year, 18 compute nodes with 4 Tesla Volta V100 32 gigabyte A6 M2 cards to accelerate exactly that, machine learning and deep learning. So if you're still around and you're part of the university or will be part of the university in January and so, you're going to be able to play on that with TensorFlow, with Keras, with PyTorch, with H2O, with MXNet, with whatever you guys want. And machine learning AI is one part. Big data analytics is, I make the difference because sometimes you really need to process 1 terabyte file in memory at one time. So of course your laptop with its 16 gigabyte of RAM, it's not enough. So then you have these kind of machines. Or you have a big box which is filled with RAM. So then you have 3-4 terabyte of RAM and you're able to load a 4 terabyte file in memory and operate on it without ever touching the disk, except for reading. So we're coming back to software. Without software, the platform is nothing. We provide around 200 packages for users. These are both compilers, libraries, and real applications. And for that, we go across many, many fields: math, physics, bioinformatics, computational physics, computational chemistry. We have general purpose, all kinds of languages that you can imagine: Rust, Go, Julia. People are wanting to use Julia. Okay, they can, and so on. So you're able to do development, you're able to do performance analytics, you're able to do performance porting, you're able to try your code with different compilers, to debug it, to visualize your huge molecules that are coming out of GROMACS or any other kind of molecular dynamics tool, and so on. So all of this, by the way, is public, so that's why there's a big link on the bottom. So this part, I think, how we manage nodes and so on, I think is not so interesting for people. Maybe just to mention that we're using automated systems and we are able to, less than 10 minutes to do the full platform at once, because it takes one node around 500 seconds and all of them can be done in parallel. So that's cool because we don't want to wait. But that's one part for node deployment. Another part is for service configuration and management, and that's done in our case with Puppet. Many other places are using other different kind of tool, but Puppet has the biggest community, and it's a very, very widespread, well-developed tool, so it's being used in our environment. And by the way, to apply a Puppet recipe on top of a server and to bring all the installation on top of a bare OS, it takes 3-6 minutes. This part I will skip. I will skip because this is what you're going to be interested about when we talk about HPC and AI in finance. There is a global race towards exascale, and everybody is joining in this race if they haven't been the ones that have started the race. So basically, the EU is committing funds for this, and all of it, everybody likes and wants and to be the first to provide the exascale level system with exascale level of performance, and finally a system which is not only able to reach this as a peak, but as an effective value. So of course this depends also on many initiatives in each place. So in EU there are many initiatives that are driving towards this goal, and I'm going to talk a bit about them a bit later. For now, I'm going to tell you that we can build right now 1 exaflop system. It looks like this. This is the Sunway Taihu Lite at 90-something petaflop, which was the best that you could get 1 year ago. So you put 10 of them together and okay, you have an exaflop system. So how much does it cost? Well, it has a 2.7 billion price tag just for the hardware. And guess what? It requires 150 megawatt of power. So I don't know how many nuclear power plants that is, but it's not effective right now. And of course, after you have the infrastructure, you need somebody able to program for 100 million threads. I tell you, that's not so easy. So in the European context, the European Union initiated a strategy, well, put in place a strategy in 2012, and with the implementation that was in the Horizon 2020. That was 2012. There was a funding scheme for HPC and so on. More recently, there were projects like IPCI on HPC big data. And the latest advance that you have heard of, and I mentioned half an hour ago, was the EuroHPC. So EuroHPC is a joint undertaking. I think it's here. So EuroHPC is a joint undertaking. It will start basically next year. In June or so, it was announced that Luxembourg is the one which will host the administrative management team. There will be public and private members. At least 13, now 14 member states have joined this initiative, and what they want to do basically is to join forces and create a European supercomputing platform. So federate pre-exascale and drive towards real exascale systems. Pre-exascale systems means a couple of hundred of petaflops. You remember we're going to have a 1 petaflop right now, so that's quite a big jump. And the driving direction is to go to exascale systems, and that not so far away into the future, so only 5 years from now. And to stimulate this, there is a budget, of course, and the budget is on the order of 1 billion euro. Actually, overall in R&D and so on, I think HPC is getting something like 2.7 billion for the next 5 years, AI 2.4, and there's big data in there, and cloud initiatives and so on. And to really drive a platform and to drive supercomputing in Europe, you also have to think about the CPU, which is still the core, is still going to be the core computational unit, even if alternatives have been proposed. So there is a direction to build a European processor based on either an ARM architecture or so on, but it needs to be there. Even if it's not going to be the fastest one on the market when it arrives, we want it. So playing together within and with the EuroHPC joint undertaking is going to be the European Technology Platform for HPC, which basically is a forum which defines research priorities. So part of the work that I've been doing 1.5 years ago was to draft some of the documents that went into the Horizon 2020 work package for 2018 to 2020. And then the Strategic Research Agenda 3, which was published last year. And the European Technology Platform, ETP for HPC, is playing a role. PRACE, the Partnership for Advanced Research Computing in Europe, is also playing a role. They've been operating the largest supercomputers in Europe, and not only in the European Union, but in Europe, because Switzerland, for example, has a very big system in PRACE. And Luxembourg became, by the way, if you have not known, the 25th country to join the PRACE. And that happened, it's now 1 year, exactly 1 year ago. So PRACE is going to have a 6th implementation phase, also starting next year, and it will play a role within EuroHPC. So future developments in Luxembourg. So we want our supercomputer, and we want it now. There is new trends in HPC, of course, so big data analytics, cloud computing, IoT, especially very data-intensive IoT, deep learning, cognitive computing paradigms. They came about. Big data is not something new, of course, but it influenced how HPC view itself, and it forced a bit of reconfiguration. So to be able to talk about this reconfiguration, when we talk about the next generation systems, all next generation systems are seen as modular. You have modules dedicated to doing one thing and doing one thing well. You have a storage module. You have a storage module which normally is going to be underneath everything else on the same storage platform. But then you have a regular HPC cluster, a booster, GPUs, FPGAs, DSPs, whatever you can imagine, neuromorphic module. That's something maybe a bit far into the future. Quantum computing will be there in some form or the other, but quantum computing, well, it has a very big ties to crypto, but it's not seen as something that will have that will solve problems like computational fluid dynamics and so on. So some traditional applications are still going to be run on the HPC cluster with its booster, GPU based or FPGA and so on. Data analytics modules, for sure, will be part of next generation systems. So for Luxembourg, the University of Luxembourg has their own data center where the Iris cluster, where you don't see it, but it's actually on some of these racks. And there's some empty spaces in here which are able to host a supercomputer of 1 megawatt in this room, 1 megawatt in this other room, and to talk to storage elements and so on, less intensive systems in the traditional air-cooled room, while these ones will be fully directly liquid-cooled and so on. So hopefully something will come next year. For that we cannot really speak right now, but the systems are there, and the Iris cluster is up and running. If things are happening, so there's been talks for some time for a national HPC big data competence center built by the ministries with stakeholders from industry, from research and so on, and to bring more than just computing services, but also knowledge and to drive the data economy. So Luxembourg has a priority right now on HPC. Financing this will come in one form or another. At the university right now, well, right now you have a bit less than this, but at the end of the year, hopefully it's going to reach the 1 petaflop mark, like I said. Hopefully in the future, we'll be able to announce something even bigger. And there's, now that you're trained, you know that there are many strategic points for strategic HPC efforts in Europe. And the University of Luxembourg and Luxembourg itself is involved in all of them. So that's been my very long talk. I think I missed my 45 minutes mark or not. Any questions? I'm really, or right now or 2 days from now, or whenever you want, you have my email, I would give. If not, valentin.plugaro@uni.lu. And I'm open to questions right now. So let's go. Yes?
Okay, so thanks for the introduction. I guess many people here are not members of the universities. How can they get access to power?
So the university provides HPC services to its members. If the university is on a joint project with somebody else, somebody else also gets access to the HPC platform. We've been in discussion with industry for purely industrial use to be able to have a contract with the university and use the university platform. And once the national center is there, the national center's main business will be to bring everybody to the platform. So if you're not able to access it right now, but you want to be considered as an advanced user that really wants to go, we will take your name and you'll be the first one to know when the platform is there.
Okay, so to summarize for now, if there is a joint project in the university, we can get it arranged with the university to get access.
The university is one of the stakeholders, but basically yes. So if you have an expression of interest, it can be done to us. We will. If we are also involved in the center in the future, that's, I mean, I cannot really speak for that, but then you will be informed.
Thanks.
Sure. Yes, Patrick?
Hi. When I started working here 3 years ago, we
Yep.
bought a Tesla K80 for our lab here in the university. And a few months later, some US intelligence agency showed up, the US Bureau of Industry and Security. They're worried about dual items and export stuff. Have they ever dealt with you? Because they came to us because of one GPU.
No.
They're worried that you use this for North Korea, whatever, you know.
Forget everything that you've seen.
Yeah. So, no, we were just surprised that they contacted our lab because of one GPU, so I wonder how they contacted you.
I have a question. What were you doing?
We were not doing anything, we were just doing research.
Buying a K80. We have a K80 since 2015. I know because I was there to install it. So we do have the K80s for a while, the K40s for even longer while, K20s, and the M2090s and 2070s since 2012. To my knowledge, there has not been any governmental agency coming and knocking, what are you doing with our
Because they contacted
accelerators.
us and the head of procurement of the university. We first thought that was actually a spam email, but it was actually genuine. and they seem to pick like random purchases and then do an inspection and want to know what you use it for. But we were picked because we only bought one GPU. So I just
That's definitely strange. When you buy 100, it's okay. To my knowledge, this has not happened.
Okay.
And we have GPUs for a long while, and a lot of people are using Ember and so on top of it for materials research for a long while.
Okay.
Somebody else? No? Yes?
Yeah. I'm curious to know, in your opinion, what would be the drivers to go from today's, let's say, 100 petabytes to tomorrow's 1,000 petabytes?
Petabytes, so storage, petaflops.
Sorry,
Petaflops?
yeah, petaflops.
The drivers? Well, the driver is the need. If there's no need for computing, nobody is willing to go there. The problem is, if there are groups, including at the university, there are groups that if you give them 100, maybe they will not be able to scale so rapidly, but if you give them 100 times more than we have right now, they're going to be happy. If you give them 5,000 times more than what we have right now, that's going to be a challenge, because at some point your software doesn't scale, so it doesn't matter how much you try to run it, it's not efficient. So there are tools, for example, NAMD is one, molecular dynamics code, which is known to scale very well. I mean, I think they run it on Taihu Lite at 800,000 processors in one execution. So finally, if you have one user able to drive the full platform, or you have 100 users able to drive 1% of the platform, you're still happy, you still go to the exaflop level of performance. So the drivers are users. I mean, they're you. You want to do data science, you want to do AI, you have an application which scales. It's PyTorch today, it's going to be something else tomorrow. Well, it was Cafe 2, then it was merged into PyTorch, but okay. So if the application scales and you have a use case for it, it's going to drive this. If you have automated, I mean, they're talking about, there was a discussion about self-driving cars. So self-driving cars are a big deal, even if only from the point of view of security, because they're able to bring you knowledge. Be aware you're going to crash into somebody if that somebody is doing a very crazy maneuver. So right now the systems are limited. A lot of people are using deep learning to try to understand these kind of situations. And driving on the road, you can only put so many cars on the road in real time. So what they're doing is they're putting the simulated cars in games, in fully immersive environments. I read about people doing this with GTA 5, okay? So, which is quite a complex environment. You have a lot of pedestrians, you have cats, dogs, you have animals, you have different kind of patterns of traffic, and people are inputting their smart car in there and then simulating it. And then you can do 1,000,000 miles in 1 hour on an HPC platform, because you're simulating, you're simulating 1 hour of driving in 1 hour, but then you're doing it at scale, so you're basically doing 1 million miles at a time. And that's why, if you have a problem that you can solve on your laptop, maybe HPC is going to be able to do it for you faster. If you have a problem, but where HPC is important is when you cannot do it on your laptop, because it will take 1 month. If it takes 1 month there, but I can do it on the platform in 1 day, well, that's a win. And that's going to be a win for everybody that is investing into HPC and into supercomputing. 100 petaflops today, 1,000 tomorrow. The drivers are the same. We need to do computing. If you read science fiction like I do, well, there's been talks of the global network. You have the internet, you have the Internet of Things, on-demand computing, and our need is not going down, it's going up. So there's a room for that.
Maybe one more question.
Yeah.
And then see if it
what is the scientific result that you achieved on your cluster that is you're proud of among all simulations that you run that have been published, and like you can say that without you?
Give me a second. This is not my laptop. Damn it. I have it in another set of slides. There was one group, so we're asking our users normally to show us what they do and to tag publications in the Orbilu system, which is tracking publications of the university. And a set of users were mentioning the HPC This work was partially done using the HPC platform. I mean, we can ask for no more than that. When they say, okay, for example, we have at least 5 ERC grant holders, their teams are operating on the HPC platform. That's a win for me. SNT, for example, they were doing analytics on the Android Play Store and many other Play Stores with app stores and so on. They were using the HPC to do this analytics, or part of the analytics for that. That's a win in my book. Yeah.
So maybe we take this offline now?
Sure, we will take this offline.
Yes, so you can still stay around, but thank you to the speakers. And,
thank you. Thank you for the invitation. No problem.
So I also want to say a few words. So just to tell you, so we are supported by the SNT and by Amazon, and both are hiring. So if you are looking for a data scientist job or something in this range, you can apply, but please refer to us so that they can measure the performance of the sponsorship. Okay? Thank you very much for coming here. See you.